Good morning, children. Today we'll learn about session 37 called as real gases. So, in this session, we'll deal about we'll understand what is mean by real gases and what is the difference between real gases and ideal gas and what is the equation for real gases, and we'll understand van der Waals gas equation. Now, in this, real gases means ideal gas. A gas obeys a law. Ideal gas, it obeys a equation called as PV is equal to RT. So here, for a particular temperature, if I draw P versus V or PV versus V, for a particular temperature, P versus V should be a constant, and this isotherms at a constant temperature will get isotherms for any gas. You should get like this. So, Ronald, this another one we have. This is an experiment called as carried out in the year 1847. A series of experiments on real gases such as hydrogen, oxygen, nitrogen, carbon dioxide. He varied pressure up to 30 atmosphere and the temperature up to 100 atmospheres, as shown in figure 2. These figures shows these results. We know that the following, that hydrogen, the product of PV increases with pressure, while other gases decreases first and then increase. So the curves are straight inclined to the pressure axis. Then van der Waals equation of state gas concluded that van der Waals are modified this PV is equal to nRT. He arrived at equation modifying that following two fundamental assumptions made by the kinetic theory of gases. One such is called as volume of the molecule is negligible compared to the volume occupied by the gas. In other words, molecules are treated as a point particles without any dimensions. This is one we are neglecting. Second one, there is no interforce of attraction between the molecules. Van der Waals agreed that these assumptions could not hold for a real gas at all at temperature and pressure. He agreed that molecules have a definite size, however small it is may be, and hence they occupy a definite space. Further, well-established cohesive force between the molecules in a liquid cannot all together disappear in a gas phase. This very fact that gases can be condensed to a liquids indicating the presence of attractive intermolecular forces. This force must depend on the distance between the molecules. Thus, he applied a correction to volume occupied by a gas due to the finite size of the molecule and the pressure exerted by the gas due to intermolecular attraction. So one such correction is for volume. Consider one mole of a gas having n number of molecules enclosed in a container of volume V. Let each molecule of a gas be a tiny odd spheres of radius r, smaller. When two molecules collide, the center molecules cannot come close together than the diameter of each molecule. Each molecule has a sphere of influence around it of radius d, that is equal to 2 times the radius of each molecule. Within, no other molecule can enter, as shown in figure called as sphere of influence. Then the volume of the sphere of influence is called as 4 by 3 pi sigma cube. Then the volume of each molecule is called as 4 by 3 sigma by 2 whole cube. When 1 by 2 is called as 1 by 8, then it is called as 4 by 3 sigma cube. That we can write as volume of the sphere of influence is equal to 8 times the volume of each molecule. Let us assume that filling the available volume V with the n molecules one by one. The volume available for the first molecule is entire volume is available, and the volume available for the second molecule is V minus S, and the volume available for the third molecule is V minus 2S. Proceeding like that, suppose if I proceeding like the third molecule, fourth molecule, fifth molecule like that, suppose I am filling the nth molecule means the volume available for the nth molecule is V minus N minus 1 into S. Now you take an average space available for each molecule, will get as, if I take all this V plus, V and V minus like that, V minus 2S up to V minus N minus 1 divided by N will get. Now if I solve that, V minus Vs by n into n minus 1, 2 by using arithmetic progression, since we know that 1 plus 2 plus 3 plus up to n minus 1 is n into n minus by 2. Now, since if I calculate this, V minus n into Vs by 2 plus Vs by 2. Since Vs by 2 is very less when compared to n into Vs by 2, therefore Vs by 2 can be neglected. Then V minus n by 2 into, instead of Vs I can write as 8 into Vm. So 8 into Vm is 4, 2 1s are 2 2s are, 2 4s are, you will get 8, then V minus n by n4 by Vm, where n4 into Vm is taken as one constant called as B, so that is called as van der Waals constant, and substitute in equation called as perfect gas equation. Instead of V, you substitute V minus B. Then the equation becomes P into V minus B is equal to RT. Another one is correction for pressure. Consider a molecule P well inside the container as shown in the figure. It is attracted by the other molecules in all directions with the same force. Hence the net force it is to be 0. Now, when it strikes on the walls of the container, then there is a molecules on one side of it which pull inward into the container. These force can be resolved into two perpendicular components. One it is parallel to the wall, another one is perpendicular to the wall. By symmetry, we note that the components parallel to the wall cancels each other while leaving out the perpendicular to the wall inwards. Thus, there is an inward pull on the molecule directed away from the wall. This net force reduces the velocity and hence the moment of the molecules will strike the wall. In other words, velocity and the hence momentum of the molecule striking the wall in the presence of intermolecular attraction, it is less than the value. Therefore, it concludes that in the absence of intermolecular attractions, clearly this will reduce the pressure exerted by the gas on the walls of the container. This reduce in pressure will depend on the number of molecules attracting the molecule which strikes the wall. Second one, the number of molecules per unit area that strikes the wall per unit time. Both the factors are proportional to number of molecules per unit volume, which in turn proportional to the density of a gas. Hence, the decreased pressure called as coercive force is called as directly proportional to the square of the density of the gas. That we know that density of a gas is inversely proportional to square of the volume. Therefore, P is equal to, if I remove the proportionality constant, I'll put a constant of proportionality called as A. Therefore, P, that pressure is decreased due to intermolecular forces, is A by V square. Hence, an ideal gas equation, instead of P, we should put it as A by V square, we should add to this. Therefore, P plus A by V square into V minus B is equal to RT is the van der Waals equation. Now, in this session, we know that we are concluded that what is meant by ideal gas and what is called as van der Waals gases we are concluded. So, some of the questions. At constant temperature, the pressure of ideal gas is doubled, its density becomes doubled. So, that is the answer. For an ideal gas, incorrect statement is molecule does not occupy any shape, no attractive force exists between the molecules, the gas move in random straight line motion, none of the above. So, none of the above is the answer. Choose the correct statement. Gases at low pressure or high pressure behaves like ideal gas. Gases at high pressure and low temperature behaves like ideal gas. Gas has high density behaves like ideal gas. None of this. A is the answer. In van der Waals equation of state for a non-ideal gas, it includes the correction for intermolecular forces. That is C, A plus P plus A by V square is the answer. In a van der Waals equation, the constant A and B with the temperature shows that remains same. A remains, B varies. A varies, A remains same. Both varies. Answer is both remains same. So to refer this session, these are the books you can refer for this session.